guys, this is Mrs. T coming at you live from Coronavirus Quarantine 2020. So we're going to work out a couple extra examples. Since you didn't have the benefit of hearing this lecture live, I thought it might help you if I worked them all out for you. Examples 1, 2, and 4 have been worked out on a previous video, so you'll have to check that out. But we're going to work on example 3. So we're looking at the differential equation dy dx equals 1 over y. Remember, this is the solution here to this differential equation, the graph of the solution. But we want to actually find that solution. And so our method of doing that is going to be separating our variables. So how does that work? Well, the first thing we always want to do is get our x's on one side and our y's on the other side. Since dy is hanging out over here on the left, my goal is going to be to move my dx to the right, and then I'm going to move my y to the other side by multiplying by y, and so that will give me y dy equals dx. And so we know our next step is, of course, to integrate. So we have to ask ourselves, what has a derivative of y? And that's going to be 1/2 y squared. And what has a derivative of dx? We can think of that as 1 dx, if that makes you feel a little better. What has a derivative of 1? That's going to be x. And we don't want to forget plus c. Plus c is the constant that we combine on both sides. On the AP test, if you forget plus c, you're going to have yourselves in a hot mess. Okay? So you want to keep your plus c there. That's very important. Our last step is to solve for y. So I'm going to multiply both sides by 2. And remember, multiplying a constant by 2 just makes it another constant. And so it's not really important that we call that 2c. We're just going to call it a different constant than we had before. And when we take the derivative, take the square root, we need to make sure that we put a plus or minus in front of that. Okay, so this is my general solution. You'll notice that it appears to be, if we have a y squared equals x, that's actually a sideways looking parabola, and that's kind of verified when you look at your solutions over here that these look like sideways parabolas. So now we're going to work with our initial condition, which is if x equals 0, y equals 1. And we're going to do that to find our c. Now this is a point of confusion for a lot of kids. If we've got this plus or minus in front here, we're essentially saying that there are two possible answers. But in this case, for this point, that is not actually true. If y is going to be positive 1, then we can't have the positive and the negative. In this case, for this point, we really only need the positive value of that square root, because if it equals a positive on this side, we can use the positive there. If this value had been negative, then we would have wanted to take the negative square root on this side. So really we have 1 equals the square root of c, which means that c equals 1. And so our particular solution is going to be y equals the square root of 2x plus 1. And so we would see that curve is the one that passes through the point when x equals 0 and y equals 1. So that kind of follows along here, like so. Examples 5 and 6 look a little bit different. You'll notice that in example 5, instead of having a dy dx, it looks like we have a y prime. So what in the world does that mean? It means x squared. Y prime is another way of writing dy dx plus y equals 0. So step 1 is going to be separate our variables. Get our x's on one side and get our y's on the other side. And so Let's first of all get that y moved over. And then because I have my dx on the bottom, I'm going to multiply that on both sides. I know that might seem a little odd because I've got x squared over here on the left, but I don't want my dx to ever be in the bottom of a fraction. Dx needs to be in the numerator. And so I'm going to cancel those dx's, and I'm going to get x squared dy equals negative y dx. And from there, I'm going to divide by x squared. And divide by negative y. Which will get us right here. And so now I'm going to take the integral of both sides. So this negative kind of bugs me. I'm going to pull it in front. And what has a derivative of 1 over y? That's going to be natural log of the absolute value of y. What has a derivative of x to the negative 2? That's going to be negative 1 x to the negative 1 plus c. Now, if we want, we can stop here. Some books will. I'm going to go ahead and solve for y because that's kind of the habit that we get into. So we'll end up with 1 over x because we'll divide by that negative 1. And we could make it minus c if we want, but remember, c is a constant, and so we can just keep it plus c if we wish. It's not going to make any difference to us. From that point, we would raise e to this power, e to the 1 over x plus c equals the absolute value of y. And when we remove those absolute value signs, we're going to get y equals plus or minus e to the 1 over x plus c. It is perfectly okay to leave that as e to the 1 over x plus c if we want, but I want you to remember that a rule of exponents is that if I'm multiplying exponents with the same base, the rule is that I keep the base and I add the exponents. So if you see a sum, like we see here, this is actually equivalent to e to the 1 over x times, that's a multiplication sign, e to the c. And so sometimes you will see us make that maneuver, but it is certainly not required. You will get used to seeing that more in the last section that we do, however. So, what are we going to try here next? We're going to figure out for this problem, on my notes here so I can see what the initial value problem was here. Oh, we don't have to find an initial value. So, we can leave our answer right here if we wish. Okay. It is also acceptable to lump that plus or minus in with e to the c if you wish, but that is enough of an answer for this problem. Because they did not ask for the particular solution, then we are not obligated to plug in an initial condition and find that. So this is the general solution right here. So I really love example 6. It's an example I usually do in class, like as a warm-up the next day, because I think it's so interesting. You'll note we kind of get in the habit of doing this XY thing. And what example 6 does is kind of force us to think, what would happen if we didn't have x and y? So what if instead of dy dx, we had dv dt? And that's what we have here, dv dt. Now you might think of v as the velocity of this person. And so dv dt would, of course, be the derivative of velocity, which is actually acceleration. So this is the acceleration of the parachutist, okay? It is how fast the parachutist is accelerating back towards the earth. So A, find a formula for the speed of the parachute. So let's find the v of t for this formula, which means if we have dv dt, that we're going to need to back that thing up. Remember, we need to think of v as y and x as t. Okay, and so what would we do if this was if these were y's and x's? Well, we'd multiply by dt on both sides. Remember, you're multiplying this whole thing by dt. And so we'd have 32 minus 0.2v times dt. And now we need our v's on the other side. We can't, because dt is multiplied by both of these things, we can't just move this term over. We need to divide by that whole thing. And so I'm going to divide this on both sides by 32 minus 0.2v. That's just an algebraic thing that we need to kind of remember. So we have 1 over 32 minus 0.2v dv equals dt. So now our variables are separated, and we need to do integration. And so we have to ask ourselves, what would have a derivative of this? So you might find that you want to use a u on that. Holy moly. Do you remember u? So if we made that a u, du would be negative 0.2 dv. Man, am I glad we did this. So I would switch this over to 1 over u, but I still have my dv, so I would need to divide by 0.2. So I could substitute in for dv with the thing I know dv equals. Negative 1 over 0.2 du. Man alive, that is a good little bit of review, isn't it, guys? Fun stuff. So where do we go from there? Well, we've got a constant. We're going to pull him in front. And then we're going to take our antiderivative. What has a derivative of 1 over u? Natural log of the absolute value of u. What has a derivative of 1? If it's dt, that's not going to be x. It's going to be, of course, t plus c. Man, this is a good one. So from there, I'm going to do a little multiplication. I keep having to make this smaller, don't I? Let's see if I can scoot that over a little bit. So let's take this guy and let's multiply by negative 0.2. So if we know that v equals e to the negative 0.2t plus c minus 32, all divided by negative 0.2, and that, as they told us in the very beginning of the problem, which you can't read very well now, but that the parachutist has an initial speed of 0 when jumping out of the plane. So v of 0 equals 0. So I'm going to multiply both sides by negative 0.2. Which is going to cancel out that 0, or 0 is just going to eat up that question or that problem there. And so this will be e to the 0 plus c minus 32 left on this side. And so that's going to be 32, if I add 32 to both sides, equals e to the c. And so what would our c be? Well, we'd have to do the natural log of 32 to get c. And so that would make our final equation v equals e to the negative 0.2t plus the natural log of 32 minus 32 all over 0.2. Very messy. So part B asks us, what happens as t approaches infinity? Well, if t approaches infinity, then we're going to have e to the negative infinity plus the natural log of 32. But the natural log of 32 has nothing on that, right? So e to the negative infinity plus the natural log of 32 minus 32 all over negative 0.2. And so what we're going to find is that this entire term right here is heading to 0 because e to the negative infinity is going to go towards 0. And so the limit as t approaches infinity of this function is going to end up being negative 32 over negative 0.2, which actually works out to be 160.